This video is brought to you by mywayteaching.com.
In this part, let us solve a very simple problem. The average depth of Indian Ocean is about 3000 meters. Calculate the fractional compression, that is delta V by V of water at the bottom of the ocean, given that the bulk modulus of water is 2.2 into 10 raised to 9 Newton per meter square. Okay, and take g is equal to 10 meter per second square. See, the pressure exerted by 3000 meter column of water on the bottom layer is given by, that is given by P is equal to HP into G, where H is the depth which is given as 3000 and P is 1000 kg per meter cube, and G they have given it as 10 meter per second square. So we can write it as 3 into 10 raised to 7 kg. Okay, meter raised to minus 1, second raised to minus 2. And here they have asked us to find the fractional compression, isn't it? That is nothing but stress by bulk modulus B, isn't it? And that stress we found it as 3 into 10 raised to 7, and even they have given bulk modulus of water, that is 2.2 into 10 raised to 10. So we get it as 1.36 into 10 raised to minus 2. If you convert it in terms of percentage, this is 1.36 percentage. So this is the fractional compression of water at the bottom of the ocean. Okay. So now let us study some of the applications of elastic behavior of materials. The elastic behavior of materials plays an important role in even in our day-to-day life. So all engineering designs require precise knowledge of the elastic behavior of materials, isn't it? It's very much important in the case of engineering designs. For example, while designing a building, the structural design of columns, beams, and supports, it all requires the strength of materials used, isn't it? How much force that that particular beam it can withstand. All that is very much necessary. See, cranes which are used for lifting and moving heavy loads from one place to the other, they have a thick metal rope to which load is attached, isn't it? The rope is pulled up using pulleys and motors. Suppose we want to make a crane which has a lifting capacity of say 10 tons or metric tons. You just consider a simple example of crane. See, suppose we want to make a crane which has the lifting capacity of 10 tons or metric tons, we can say, because 1 metric ton is 1000 kg. See how thick that steel rope should be. So we obviously want that the load does not deform the rope permanently, isn't it? So therefore the extension should not exceed the elastic table. So we already studied in the table that the mid steel has a yield strength of if the force exceeds this limit, then the rope will break. It is having a yield strength of 300 into 10 raised to 6 Newton per meter square. So thus the area of cross section of the rope should be at least greater than or equal to that load by the stress which is given by mg by sy. So here we have considered 10 raised to 4 kg and G is 10, and that yield strength is given by 300 into 10 raised to 6. So if you simplify this, that area will get it as 3.3 into 10 raised to minus 4 meters square. Okay, corresponding to a radius of about 1 centimeter for a rope of circular cross section. Generally, a large margin of safety is provided. Say, for example, a factor of 10 in case of load. So that much safety is very much necessary because it may cause some dangerous events. In order to avoid from all those conditions, a large safety is provided. Thus, a thicker rope of radius about 3 centimeter is recommended. Even though 1 centimeter is sufficient, in order to provide the extra safety, a rope of 3 centimeter is considered. A single wire of this radius would practically be a rigid rod, so the ropes are always made of a number of thin wires which are braided together like in pigtails for ease in manufacturer flexibility and strength. Okay. A bridge has to be designed such that it can withstand the load of that flowing traffic, the force of winds, and even its own weight. Similarly, in the design of buildings, so in case of bridge also, the knowledge of the materials is very much important because it should withstand that traffic. Because okay, every day it will a large amount of traffic. The bridge is subjected to a large amount of flowing traffic, isn't it? Even it should withstand the force of winds. And even its own weight also. And not only in case of bridges, and another application is in the design of buildings. In this particular case, we'll use beams and columns. Okay, the use of these beams and columns are very common. So in both the cases, the overcoming of the problem of bending of beam. Okay, bending of beam as well as columns, in order to overcome that is very much important, isn't it? That problem should be solved. So the beam should not bend too much, or even it should not break. So in order to provide this safety, this knowledge of elastic materials is very much necessary. Okay, so you just consider a simple beam here. Let us consider the case of a beam loaded at the center and it is supported near its end. Is loaded here at the center and supported near its end. A bar of length L, you can see here, and breadth B and depth D, when loaded at the center by the load W, it sags by an amount. See, actually, in the beginning, it was this, a straight rod, but due to this applied weight, it sags. So, how much? So, that is given by this symbol, which is given by W LS by 4B DQY. So this here B is the breadth, D is the depth, L is the length. Okay. Even this relation can be derived using the calculus method. See, in order to reduce the bending for a given load, one should use a material with a large Young's modulus. For a given material, increasing the depth rather than the breadth is more effective in reducing the bending, since this the sag sigma, that is proportional to d raised to minus 3 and only to b raised to minus 1, and length L of the span should be as small as possible. But on increasing the depth, unless the load is exactly at the right place, the D bar it may bend. The D bar, it can also bend.